Why do x86 CPUs only use 2 out of 4 rings? So at a Linux or Windows-based x86 systems only use ring 0 for kernel mode and ring 3 for user mode. Why do processors even distinguish 4 different rings if they all end up using just 2 of them anyways? And has this changed on ARM64 architecture?
There are 2 primary reasons. The first reason is that, although the x86 CPUs do offer 4 rings of memory protection, the granularity of protection offered thereby is only at the per segment level. That is, each segment can be set to a specific ring, privilege level, from 0 to 3, along with other protections like write disabled. But there are not that many segment descriptors available. Most operating systems would like to have a much finer granularity of memory protection. Like for individual pages. So, enter protection based on page table entries. Most if not all modern x86 operating systems more or less ignore the segmenting mechanism, as much as they can, anyway, and rely on based protection. This is spec-T by flag bits, which are the lower 12 bits in each, plus bit 63 on CPUs that support no execute. There is one for each page, which is normally 4K. One of those flag bits is called the privileged bit. This bit controls whether or not the processor has to be in one of the privileged levels to access the page. The privileged levels are PL0, 1, and 2. But it's just 1 bit, so at the page-by-page protection level the number of modes available as far as memory protection is concerned is just 2. A page can be accessible from non-privileged mode, or not. Hence just 2 rings. To have 4 possible rings for each page, they will have to have 2 protection bits in each page table entry, to encode one of 4 possible ring numbers, just as do the segment descriptors. They don't. The second reason is the goal of OS portability. It's not just about x86, Unix taught us that an OS could be relatively portable to multiple processor architectures, and that was a good thing. And some processors support only 2 rings. By not depending on multiple rings in the architecture, the OS implementers made the OS more portable. There is a third reason that is specific to Windows NT development. NT's designers, David Cutler and his team, whom Microsoft hired away from DEC Western Region Labs, had extensive previous experience on VMS. In fact, Cutler and a few of the others were among VMS's original designers. And the VAX processor for which VMS was designed, and vice versa, does have 4 rings. VMS uses 4 rings. In fact, the VAX has 4 protection bits in that, allowing combinations like read-only from user mode, but writable from ring 2 and inner. But I digress. But the components that ran in VMS's rings 1 and 2, record management services and the CLI, RESP, were left out of the NT design. Ring 2 in VMS really wasn't about OS security but rather about preserving the user's CLI environment from one program to the next, and Windows NT just didn't have that concept. The CLI runs as an ordinary process. As for VMS's Ring 1, the RMS code in Ring 1 had to call into Ring 0 fairly often, and ring transitions are expensive. It turned out to be far more efficient to just go to Ring 0 and be done with it rather than have a lot of Ring 0 transitions within the Ring 1 code. Again, not that NT has anything like RMS anyway. But why are they there, then? As for why x86 implemented 4 rings while OS didn't use them, you're talking about OS of far more recent design than x86. A lot of the system programming features of x86 were designed long before NT or true Unix-ish kernels were implemented on it, and they didn't really know what the OS would use. It wasn't until we got paging on x86, which didn't show up until the 80386, that we could implement true Unix-ish or VMS-like kernels without rethinking memory management from the ground up. Not only do modern x86 OS largely ignore segmenting, they just set up the C, D, and S segments with base address 0 and size of 4 GB. F and G segments are sometimes used to point to key OS data structures. They also largely ignore things like task state segments. The TSS mechanism was clearly designed for thread context switching, but it turns out to have too many side effects, so modern x86 OS do it by hand. The only time x86 NT changes hardware tasks, for example, is for some truly exceptional conditions, like a double fault exception. Re x64, a lot of these disused features were left out. To their credit, AMD actually talked to OS kernel teams and asked what they needed from x86, what they didn't need or didn't want, and what they'd like added. Segments on x64 exist only in what might be called vestigial form, task state switching doesn't exist, etc., and OS continue to use just 2 rings.
If you wonders upon the channel, please consider subscribing.